Hello and welcome back to Dragon Mathematics. I'm Dragon and this is the mathematics. So we're doing graphing, functions, and transformations. Okay. In the previous video, I sketched a few graphs for the purpose of demonstration, but let's get a little bit more rigorous about it in this one. So in this video, we will cover graphing by plotting points, recognizing basic graph shapes, and understanding transformations, which is another fundamental math concept which applies to many things. So one of them, let's see, types of transformations. We have shifts, reflections, stretches, and compressions, or you can think of it like the opposite of stretching, so shrinking. And let's get right into it, right? So, graphing by plotting. I feel like my handwriting's gotten worse today. You can let me know based on previous videos, is my handwriting worse? So, this is the most basic way to graph a function. If we have a function like this, f of x equals 2x minus 1, well, we can immediately plot that by just doing this little table of x's and y's and saying, okay, what is, if I have an x of minus 2, an x of minus 1, x of 0, x of 1, x of 2, what will the y be for each of these situations? Well, let's extend this. If x is negative 2, then y is 2 times the x, which is 2 times minus 2, minus 1, which will be negative 4 minus 1, that's negative 5. And then 2 times the x, negative 1, minus 1, will be negative 2 minus 1 equals negative 3. 2 times 0 minus 1 will be 0 minus 1, which is negative 1. And for the positives, 2 times 1 minus 1 gives me 1. 2 times 2 minus 1 gives me 3. And then what we can do is plot that. So I'm going to say 1, 2, 3, and you can infer the rest, so I'm not going to label them. But, right, so the points that we just found would be negative 2, negative 5. So I'll go here on the x, over here to negative 2, down to negative 5, 1, 2, 3, 4, 5. Plot that point. So that's negative 2, negative 5. I'll go to negative 1 in the x direction and negative 3 in the y. 1, 2, 1, 2, 3. All right. And we'll go to 0 in the x, which is right here. So this will be on the y-axis, and this will be 0, negative 1. And then we have a point at 1, 1. So 1, 1 is right here. And we have another point at 2, 3. So 1, 2, 1, 2, 3. So we connect these points to tab and make it a straight line. And so what we just graphed is a linear function, 2x minus 1. And you connect the points with a straight line. You can see it's linear. It also makes sense because the way we identify these parts, the slope is 2, so it's rising here. It goes up 2, so 1, 2 over 1, 1, 2 over 1, so it's increasing. That's why it's positive 2x. And then this minus 1 is the y-intercept. So you can see down here at negative 1 is where it crosses the y-axis. It's just a quick check to verify that that's correct. And we can do the same thing for a quadratic function like this. So we'll make a quick table of x's and y's. Let's do negative 6, negative 4. Wait, no, negative 6 squared will be 36. Let's not do that. Let's do negative 3, negative 2, negative 1, 0, 1, 2, 3, right? So if we square negative 3, we'll have negative 3 squared, and then we subtract 2, we'll have 9 minus 2 is 7. Negative 2 squared minus 2 will be 4 minus 2 is 2. Negative 1 squared minus 2 is 1 minus 2, which is negative 1. 0 squared is just 0. Minus 2, that gives us negative 2. 1 squared is 1. Minus 2 will give us negative 1. 2 squared minus 2 will be 4 minus 2. That gives us 2. 3 squared minus 2, again, 9 minus 2 is 7. And now let's keep this in mind when we graph this quadratic. So at -3 in the x direction and 7, 1, 2, 3, 4, 5, 6, 7. So let me move this actually. 1, 2, 3, 4, 5, 6, 7 right there will be our first point. Then we have -2, 2. So again, this is -3, 7. This is -2, 2. Next is -1, -1. Then we have 0, -2 right here. Then it mirrors over the y, which makes sense. +1, -1, 2, +2, 1, 2 here, 1, 2 here, +2, +2, +3, 1, 2, 3, 7, which is right here. And we connect those, and it should make a nice little parabola. This makes sense to us because of that x squared in there. That's why we see this shape. Okay, so that's just an example of plotting points, how to graph that way. And so the more you work with various functions, the more you'll start to recognize these basic shapes of a function. Like we have a linear function, as we've done a few times now, which is a straight line. And the equation looks like mx plus b. The graph looks like a straight line. Okay, straight line. And then we have our quadratic, right, which is a U shape. And the equation looks like this. Some constant in front of the squared term, some constant in front of the x term, and some constant by itself. And how does that look? It usually looks like this, right? Some sort of U, or it could be going in the opposite direction, negative direction. Our cubic is the S-shaped function, which has that same form as the quadratic, except one more power there. And that would look like this, right? Either you have that, either you have that, or you might see something like this, right? With that symmetry over the origin itself. That's the cubic, and the symmetry over the y-axis. That's our quadratic. There's the square root function, which is just like half, we'll call it half of a sideways parabola. We have f of x is equal to square root of x. Looks like this, right? It could look like that. It could look like this. It could look like this. Oops. Depending on circumstance. And then the absolute value function has that V shape to it, like that. Or it could be negative. Might be wondering how, if it's absolute value. Well, if you have this, then all the negative values that go in are going to become positive, but then there's a negative sign in front of that, so it's going to get flipped over the x-axis, and they will all become negative. So those are some common basic functions that you'll see. And then the next thing to do is to think about transformations, as I spoke of. So transformations are a way to modify those basic functions I just drew by shifting, reflecting, stretching, compressing. So manipulating is a word I'll probably use throughout this video. And so what you do is you start with a parent function, which would be our basic function I just mentioned. So if we have y equals x squared, or y equals the square root of x, or y equals absolute value of x, okay? Then here, start with a parent function, then apply a transformation to get a new related graph. So first one we'll talk about is shifts. And so that's exactly how it sounds, right? If you want to shift the graph vertically, so up or down, the rule is to shift a graph vertically by c units. You should, to shift it up, we'll add c to the outside of the function like this. right? This is our basic function that I mentioned. What did I call it? Parent function. And then we'll add some constant to shift it up, and to shift it down, subtract c from the outside of the function. So y equals f of x minus c. We'll shift the graph down. And a quick example of that, say we have a parent function of f of x equals x squared. Okay, well, that's going to look like this, something like that. And we want to shift it up 3 units. What are we going to do? We're going to say f of x equals x squared plus 3 units. And now it's going to look like this, 1, 2, 3. Same exact shape, just shifted up 3. And, or here, let me write this as g of x, since it's a new, we'll look at it as if it's a new graph, new function. Or say we want to shift it down 2 units. Okay, we'll do x squared minus 2, and then the new graph, since we started here with our parent function, would be 1, 2, same exact shape, but shifted down 2. So what is happening when you do a vertical shift is that every y value on the original graph is moved up or down. Either here it was plus 3 up or minus 2 down. So that is the definition of a vertical shift. And then the next shift, you might have guessed it, horizontal shifts, and those will go left and right on the graph. I wrote the word graph. The rule here is, so to shift the graph horizontally by c units, all right? To do it to the left, we're going to replace, this is slightly different than the vertical shift. Replace the x with x plus c if you want the graph to shift to the left. And so it would look like this. Y is equal to f of x plus c. So see now for the vertical shift, we were adding the c out here, and for the horizontal shift, we're adding it to the actual argument of the function x. So now it's f of x plus c inside the function. And to go to the right, you replace x with x minus c. So what parent function was y equals f of x. Now it's y equals f of x minus c. And that'll shift it to the right. So it's a little counterintuitive. When you're shifting the graph in the x direction, plus some number is going to shift it to the left. You might expect that a plus shifts it to the right, but it shifts it to the left. It's just something you have to remember. And minus some number will shift it to the right. So the example, we'll do the same parabola, right? Parent function is y equals f of x, which here f of x is x squared. And I can just leave this out. So we'll do, right, here's our original graph, parabola, basic parabola x squared. And then say shift left 3 units. Well, that will look like this. G of x equals x plus 3 all squared. And so what's that going to do to the graph? It's going to shift it to the left 1, 2, 3. And so this is our g of x. Okay? This is f of x, remember? And then if we wanted to perform the transformation that shifts the graph to the right, say 2 units, then we would have this new function h of x equals x minus 2 squared. Remember, to go to the right, you subtract, and go to the left, you add. It's kind of weird and counterintuitive, but you just got to get used to it. Here, you may have guessed it, 1, 2 to the right. It's our parabola shifted to the right. There's h of x right there. So yeah, it's sort of weird how it's different for vertical shifts and horizontal shifts. But the way I always looked at it was, so think about it. We have y equals f of x, right? Our parent function or our original function. If I add something to the y, right? So y equals f of x. Well, if I add out here, outside the function, I'm adding, see how I'm adding to the y? Well, then that's going to affect the y. So, right, something moves up or down, plus c, minus c in the y direction. And if I add something to the x here, see, that's going to shift it left and right. And it's just a weird happenstance thing that when you add 2, it shifts to the left 2. And when you subtract 2, it shifts to the right 2. So really all you have to think about is the fact that when you shift something horizontally, it's counterintuitive. And then we have reflections next. So first, a reflection across the x-axis. To do that, the rule is that you multiply the outside of the function by -1, right? So y equals negative f of x. And that's going to flip it or reflect it across the x-axis. So it's going to flip it or reflect it vertically. It's going to flip it along the y, but it's going to flip it across the x-axis. So a quick example is if your parent function is f of x equals square root of x, that original function, the parent function, looks like this. Okay. Reflection across the x-axis is going to be f of x equals negative square root of x. I'm just going to put y. So the reflection across the x-axis, well, now will be down here, right? So it flipped across the x-axis. And then if we do it reflection across the y-axis, that rule is, again, instead of just multiplying, we're replacing x with minus x. So in the argument of the function. So same parent function as the last example. If f of x is square root of x, we know that looks like this now. If I reflect across y-axis, right, or along the x-axis, this will flip from here to here, and it'll look like this. F of x equals square root of negative x. See how before we put the minus sign in front, and now we replaced x with negative x. And so with this we should also write f of negative x technically. So it'll flip over here. So yeah, this is often less visually obvious for some functions, but it's important to understand just by looking at those basic functions. And then what else do we have? We have stretches and compressions. So the rule is you multiply the outside of the function by some constant. Here we're going to call it a, by some constant a. So it'll look like this, a times f of x. You can put a little star there if you want to think multiply, but so a times f of x. And so for a vertical stretch, this one's slightly more complicated to wrap your mind around, but I believe you can do it, right? For a vertical stretch, and that's when I'm putting absolute value of a to be technically correct. If the constant, its magnitude, is greater than 1, so if it's some stretching factor, right, 1 times f of x, we'll just leave it f of x. 1.5 f of x will stretch it to be 1.5 times the f of x. So if this a, same works for a negative, that's why negative 1.5 f of x is going to be, you know, the opposite direction, but still stretched 1.5 times, just negative. So the point is, if your magnitude or the absolute value of this a is greater than 1, the graph will get taller and sort of stretched vertically. So if that, then graph gets taller, stretched vertically. Okay, and then we have a vertical compression. And that occurs if absolute value of a is less than 1, but also greater than 0. So right? That means 0.1, 0.5, 0.8, 1/2. All of these values are going to make the graph shorter in the vertical direction. So graph gets, this is if A is any of these, is what I'm saying. Graph gets shorter slash compressed vertically. Okay, so let's do an example so that can be clear. If we once again use parent function of absolute value of x, right? The original graph looks like this. And if you vertically stretch it by a factor of 2, so vertical stretch by factor of 2, then the new function will look something like this. So this would be g of x equals 2 times absolute value of x. See how it looks taller or stretched? Then vertical compression by a factor of 1/2 will look like this. It's more flattened. 1/2 of your original function is going to make it shorter, compressed vertically. Okay? Then we have horizontal stretches and compressions. And the rule here, once again, when it comes to modifying the x, manipulating the input, we're going to replace x with, we'll have x over b inside the function. So it'll look like this, f of x over b. And so for a horizontal stretch, that's when b now, the absolute value of b, is greater than 1. The graph gets wider or stretched horizontally, right? We could say horizontally. And then horizontal compression will be if b is between 0 and 1, right? So if b equals 0.2, 1/2, 1/4, whatever, the graph gets narrower or compressed horizontally. So we'll do an example of that. We're going to use the parent function again of f of x equals absolute value of x. So that's what that looks like. If we do a horizontal stretch by a factor of 2, then the result will be a graph now looks like this, right? That'll be g of x equals absolute value of x over 2. So remember, if it's x over b. So our factor is 2. If you replace x with x over 2, you could also think of this as f of x over 2, but we're just making a new function called g of x. Okay, it's going to get flattened like that. And then for horizontal compression by a factor of 1/2, we will get, and it's starting to get weird, but it's going to again look like a previous graph we drew. But this is h of x equals what is x over b. So our b is 1/2, 1/2. Okay, and I know that looks weird, but this is equivalent to absolute value of 2x. So that part is a little weird to think about, but the idea is just that if you're stretching something horizontally by a factor of 2, what you're doing is dividing x by 2 or replacing x by x over 2. And if you're doing a horizontal compression by a factor of 1/2, then you're dividing x by 1/2 or replacing x with x over 1/2, which x over 1/2 just turns out to be, right, this is the same as x over 1 times this upside down, which is 2 over 1, which is the same as 2x. So to stretch something horizontally by a factor of 2 means to replace the x with x over 2. To stretch something vertically by a factor of 2 means you're just multiplying the x by 2. So the pattern you've seen is when you do something in the y, like a vertical shift, you just add 2 to the outside of the function. And if you want to do a horizontal shift of 2, 2 to the right, say, well, then you replace x with x minus 2 to shift to the right, and that's in the argument. So, yeah, so generally you should apply transformations in this order. So horizontal shifts first, then stretches and compressions. The reason you won't see reflections in here is because you can just think of a reflection as a stretch or a compression by -1, right? And then vertical shifts. The reason I say that is, here I'll say, vertical reflections can be thought of as stretches or compressions by just -1. So remember right here I said, if A is greater than 1, or A is between 0 and 1, but I never mentioned what if A were 1. Well, if A is 1, then no stretch is actually happening. If A is -1, no stretch is actually happening, and it's back to our flip that we spoke of, reflection. So I guess what I'm saying is if you have square root, then you hypothetically were to say, oh, I'm going to stretch it by -1. Okay, well, how would you write stretch by -1? Well, you would write -1 in front. That would be your A times square root of x. Well, when you do that, what's going to happen is it's going to flip like that. Okay? I hope that makes sense. Now, what we're going to do is some examples. So examples of combining different transformations. So to describe the transformation from f of x equals x squared to g of x equals -2x plus 1 squared plus 3. Okay. To go from here to here, first step, we would start with f of x equals x squared. So let's draw it. So 1 times 1 is 1, or 1 squared is 1, 2 squared is 1, 2, 3, 4. All right. Here's f of x equals x squared. And what I'm going to do is horizontal shift left. So luckily I have this thing is very handy. Right, first thing, like I said, is a horizontal shift. So we see here that x plus 1, that is a shift of 1 unit to the left. So that's the first thing I'm going to do. Horizontal shift left 1 unit. And so the function will now be this. Okay. I'm going to shift it. Luckily, I do not have to redraw it. Thank God. And 3, next step will be vertical stretch here, this -2 now that's occurring on the function. So vertical stretch by a factor of 2. Not going to deal with the minus yet. I'm just going to do it one step at a time. So I'll take the updated graph and stretch that by a factor of 2. So here's what our function is going to be now, right? I'm going to stretch it by a factor of 2 by doing this. It won't be perfect, but I don't want to calculate each actual point because it would take too much effort. But a quick sketch of it would look like this. So here's this. All right, that's that function now. And then the next step will be that negative sign we have to deal with. So reflecting across the x-axis or along the y-axis, whatever you prefer to call it. Two different ways to think about it. It's the same thing. Reflecting this across the x-axis, now we'll add that little minus sign there. And the result will be, take this, reflect it, pretty close. Okay, so now it's reflected. And then we're going to do, let's go back up here and look, make sure we're doing what we need to do. And here we have a vertical shift of +3. So that's what we're going to do next. Vertical shift up 3 units. And now the function will be updated to this, +3. So I'm going to take my updated graph, update it again, and by shifting it up 3. 1, 2, 3. And now we have the graph g of x that we were looking for, right? So that's how you would do it. And what I'm going to do now is pull up Desmos, okay? Desmos is amazing for understanding transformations like this, which you'll see right now why. So if I start with the square root of x, right? Square root of x. Okay, so say that the function we want to work with is we want to go from square root of x. So just like we just did f of x equals x squared, going to g of x equals negative 2 x plus 1 squared plus 3. Well, this time let's do f of x equals x squared here, going to h of x equals this square root of 2x minus 1 plus 5, right? So let's say we want to get from the red graph to the green graph. The first thing we would do is start by multiplying the input variable x by 2. So we're looking at red right now. Multiply it by 2, you see it gets stretched vertically. See how it moves? It's the same graph, but stretched vertically. So if I put 4, it'll be stretched by even more. 8, it'll be stretched by even more vertically. And this is why Desmos is perfect for understanding transformations, because you can watch them happen live. Drawing them yourself is helpful, but Desmos is a really good tool for demonstrating it to yourself. So 2 times the x. Okay, now we got that vertical stretch happening. And then the next thing we want to do is I can see this minus 1 is going to move it to the right 1. Remember, it's not going to go to the left, it's going to go to the right. So minus 1 inside the square root. You can see right here it shifted over 1. Okay, hello. Real quick, I didn't notice this until I was editing, but yeah, in the video you're watching right now, I was doing this square root of 2x minus 1 like that, and then shortly after we had the plus 5. But you'll notice actually that this right here, the red graph, didn't actually go to 1 because I wasn't paying attention, but it goes to 0.5. And you just have to be careful with this, because what's happening is what's under the radical here is 2 times x minus 1, as opposed to 2 times the quantity x minus 1, which if you see here, x minus 1 would now shift to the right 1. But without the parentheses, what we pretty much have, let me put tablet back up. The reason that happens is because what we have going on is 2x minus 1 is not the same as 2 times x minus 1 as a quantity, okay? This actually, if we were to rewrite it similar to this one on the right, then it would be this 2 times the quantity x minus 1/2, right? So it just adds a little more complexity to graphing that. So yeah, the way I demonstrated it, Desmos shows you something true, but what I'm saying is speaking about a graph that shifts to the right 1, when in reality, if you have f of x equals square root of 2x minus 1 plus 5, then you'll just have to make sure that when you're graphing this, you don't just say, okay, it's x minus 1 right here. That means the graph is going to shift to the right 1. That's not the case, because you want to know what is specifically happening to the x. This minus 1 is 1 being subtracted from 2x. So if 1 is being subtracted from 2x, well, actually, what's happening is 1/2 is being subtracted from 1x, if you think about it, right? If you pull a 2 out of this. So just be careful of that. It got me, so it could very easily get you as well. But it's a good learning opportunity. So anyway, back to the video. I'll do it again so you can see. So it's here, minus 1. Now it's moved over. And then outside of the square root, we have a plus 5. And now it gets moved up here to be on top of the green one. See? So, I mean, you can do this, your imagination can just run wild, and you can do, okay, what is x? That's the parent function x squared, the original function x squared. Well, what does x minus 12 squared, all of that times a negative 1/2, all of that minus 0.03, that's not very visible, 0.5 or 5, right? What would that function look like? It's just really useful. So that's all I have for that. And that's Desmos. I love it. I think it's a great tool for just, like I said, being creative and thinking about functions and transformations. There's a lot more you can do with Desmos, but definitely useful for this. So anyway, today we learned how to graph functions by plotting points, how to recognize basic shapes, how transformations affect graphs and how to apply them ourselves. Transformations are powerful and essential for more advanced math, and you just have to practice. The best way to get comfortable with these is to do it, do it by hand, use Desmos, and yeah, just watch how the changes affect the graph. Makes it a little bit more fun and more interesting when you do it yourself. And thanks for watching. I hope you found it useful. If you did, like and subscribe and share this with anyone that's learning pre-calc. And I'll see you in the next video. Thanks. Bye.